How distant can we see? Here's a presentation outline. We will present some ground rules which define the optical and gravitational horizons, and a derivation for the optical horizon in an expanding universe, without matter, with matter, and for flat and curved systems. We'll present some sample calculations, evidence of curved spacetime from ancient stars. We'll estimate distant objects from the redshifts, and we'll have a little bit of fun with Einstein lensing, evidence for curved spacetime. The cosmic horizon, R sub h, some ground rules. The cosmic horizon is defined as the furthest distance from which light can travel to an observer, given perfect optical conditions and a wonderful telescope. That's the optical horizon. Light beyond the optical horizon cannot be observed. Neither can gravity beyond the optical horizon. We will presume a constant light speed c, and t is the time from emission to the observation. Recent observations suggest that, on the average, Minkowski spacetime holds locally. Sort of flat. That's reference 3. According to Einstein, the light horizon is the same as the gravitational horizon. Recent results from LIGO indicate the gravitational information travels very quickly. Our universe is homogeneously and isotropically sprinkled with matter, so the optical horizon should be the same in all directions. Information, including the gravitational influence of matter outside the optical horizon, will be a loss to the observer. In an expanding universe, the volume outside the optical horizon is increasing. For a contracting universe, this volume decreases with time. How about this straightforward description of the cosmic horizon? That's equation 1. This is often termed a light-like horizon distance and describes a static, flat universe without matter. Recent publications by those claiming equation 1 describes our universe with matter is listed under further reading. That's references 4 and 5. And here we have a NASA image of the extreme Hubble deep field view. A beautiful, beautiful presentation. And you note the little red dots, which are those tiny squares A, B, and C, which are blown up on the top right, A, B, and C. The little red dots might be galaxies close to the optical horizon. And here we present a very famous graph from Hubble presentation in 1929. That distant galaxies recede with greater velocities than the nearby galaxies, as shown on this primitive graph. The optical horizon for an expanding universe without matter. The escape velocity for light for a person on Earth searching for the optical gravitational horizon can be calculated beginning with classical physics, as presented in reference 7. Allowing for the conservation of energy, and with Newton's law of gravity as equation 2, we can arrange this to equation 3. The optical horizon as observed from our Earth, at the extreme limit where velocity equals light speed, the distance at which light is not under any influence of objects further, is presented in equation 4. This is also termed the Schwarzschild radius, and this comes to us from Einstein's physics. An excellent derivation of the Schwarzschild radius can be found online in reference 8. Now it's time for some matter and some gravity. Describing our universe as a dust-filled, homogeneous matter ensemble, with the matter equals density times a volume, where V is the volume of a three-dimensional sphere, is presented in equation 5. Here we use the definition of the critical density with the Hubble constant h sub naught as presented in equation 6. More time for some gravity, matter, and expansion. This allows us to use the normalized form of the matter density as omega sub m, and use this in equation 7, where the expansion factor is in 3 dimensions. We normalize this because we presume the universe consists only of matter and spacetime, omega sub k, so that equation 8 holds, as the case for the normalized parameter, which is presented in reference 9. The result is a horizon which is dependent on this expansion factor and inversely proportional to the Hubble constant and the matter density, omega sub m, as presented in equation 9. If we allow light speed to be infinite, then the optical horizon becomes infinite. This is consistent with Newtonian universe. And if the Hubble constant is very small, the optical horizon is also very large, which allows us to trust equation 9. How about for a flat universe where k equals 0 from the Friedmann viewpoint? We will now examine a horizon for the special case of k equals 0. That's a flat universe, a geometrically flat universe. Some reports suggest this is approximately true today, as in reference 3. We will begin with the Friedmann relationship without the cosmological constant, that is, no dark energy, as presented in equation 10. And then derive the special case for a flat universe, again allowing k equal to 0. If we allow k equals 0 for a flat universe, then substitute with the current matter density, rho sub naught, this reduces to our situation in equation 11. Rearranging Hubble and introducing omega sub m for the normalized matter density and taking the square root of all this, we get equation 12. And after some more math and more substitutions, allowing k equals 0 for a flat universe, we arrive at this collection called equation 13. But note that several terms cancel here, and the result is, for a flat expanding universe with matter, we end up with the simple equation, equation 14. And what does this relationship, equation 14, really refer to? Does this mean that the optical horizon is traveling faster than light speed? Yeah, sort of. Remember that the solution is true for a person standing on Earth collecting light from a receding emitter, while the observer is also traveling in the opposite direction. This relationship, equation 14, describes the distance between a stationary observer and the horizon. This is the light speed horizon in the presence of matter. And we should also remember that the Earth is moving away from the emitter with the same velocity as that distant galaxy. So to calculate the proper optical horizon, we need to adjust for our velocity, which we do as equation 15, where r sub h is the true optical horizon for our universe. Now the optical horizon for a flat universe with matter. The instantaneous optical horizon is really only true for an observer in a flat universe containing a bit of matter who can record the emission and detection simultaneously. This is an imaginary situation. Some people will infer that the optical horizon is greater than light speed, and this means that spacetime itself is expanding. But what the math really means is that one cannot discern between an expanding spacetime and a rapidly moving, very distant galaxy. Equation 15 simply represents the optical horizon and nothing more. Can we correctly guess the universe age? Astronomers have recently published observations of stars that are about 14.5 billion years old from spectroscopy data in reference 10. This value is older than many current estimates of our universe, which is estimated by Astrophysics to be really only about 13.7 billion years old. It's equation 11. Sorry, reference 11. A greater value than 13.7 has also been calculated from radioactive decay data by a geologist, as presented in reference 12. Another study found a local star, 13.2 billion years old, calculated from the abundance of elements heavier than lithium, in reference 13. We presume the popular universe age of 13.7 billion years is too low. So for our simple calculations, we will round up and use 15 billion years to estimate the galaxy age from only the redshifts. Oh, here we present a local metal-poor star. This is an extremely old star, Methuselah, which resides in our Milky Way galaxy. Is he older than our universe? Cannot be older than our universe. How far is our optical horizon? Should we expect a universe age older than the oldest star? Certainly we should. Using our new equation for a flat universe, equation 16, and allowing the age of a universe to be 15 billion years old, equation 17, we end up with the optical horizon in one direction as 45 billion light years. And some recent calculations based upon the cosmic microwave background data suggest the optical horizon is closer to 46 billion years. So we are consistent with some calculations from the CMB data. If we know the universe age, we may calculate distances from using only the redshifts. That's a much simpler task than estimating distances. We remember the cosmological distance is related to the galaxy age, that is, the time light took to travel to us. Estimates of distance age are fraught with difficulties. One can see the error estimates of distant supernova type 1a presented in the next figure. Figure 4, the luminosity distance versus a redshift correlation. We see that estimates of very far distant supernova are really extremely suspect. The simple sigmas associated with these distances are always very large, beyond a redshift of about 0.3, 0.4. Estimating the distance with redshift. We can also use a relationship published by Carmelli to quickly calculate the age of the emitter, reference 17. This only requires a good guess for the universe age, using equation 19. We will use t sub 0 of 15 billion years for a demonstration. This simple formula will give us an estimate of the emitter age after the Big Bang. Now, quasars are the most distant objects we can detect. And here we have a plot of this Carmelli function estimating the year of emission using only the redshift in the x-axis. And here we have an example of a very, very distant quasar with a redshift of 5.82. And we can estimate that this quasar started emitting 600 million years after the Big Bang. A very, very young quasar. The age and distance of an emitter can also be roughly estimated from another formula using galaxy redshifts. A commonly used redshift-distant relationship is given by equation 20, which requires the Hubble constant and requires an estimate of the matter density and, of course, the redshift. We suggest using the Hubble constant of Sandage, which is about 63.2, and a very low matter density of less than 0.1 for calculations using equation 20. This will give us the age of the emitter after the Big Bang. Oh, and here's an example of some very old stars in our own Milky Way, as provided by NASA. This really is a very, very beautiful ensemble of very old stars in our Milky Way, and they're supposed to be 12 to 13 billion years old. Measuring the distance with redshift again, we can also use another relationship published by a student of Carmelli to calculate the relative age and distance of the emitter, reference 17. This includes a guess for the universe age as presented in equation 21. On the left side, one uses a Hubble constant of 72 and on the right side, one uses a Hubble constant of 62. This will give you an estimate of the emitter distance from the Earth, good out to about redshift of 2. These simple methods for calculating the age of galaxies presume a flat universe, but there is abundant evidence that our universe exists in curved spacetime. For instance, the observed delay in signals received from the Cassini satellite orbiting the planet Saturn. An illustration of that is presented by NASA. And here we see NASA giving an illustration of what they found out to be gravitational redshift and a significant delay in signals received from the Cassini satellite when it was orbiting Saturn as the signal passed by our sun. Nice illustration. More evidence for curved spacetime. This comes from many observations of Einstein lensing around galaxies, presented in reference 19. The next frame presents a NASA photo which clearly displays evidence for light bending around a distant galaxy. This is a nearly perfect Einstein lens around a distant galaxy, as in Figure 9. Our universe exists in curved spacetime, so the light horizon is also spacetime dependent, as well as being matter density dependent and Hubble spacetime dependent. A graph of this more complicated version of our optical horizon is presented as the next figure, presenting both flat spacetime and curved spacetime. Note that for our universe with curved spacetime, the size of our universe becomes absolutely enormous. And this is presented in Figure 10, where we use matter density of 0.05 and the Hubble constant of Sandage of 62.3. One could see there is very, very great difference between a flat universe and a curved spacetime universe. Here we have another example for Einstein lensing. It's another figure from NASA public files. Beautiful photograph. To summarize, we presented a simple method for calculating the optical horizon, R sub h, presuming a flat universe with homogeneously scattered matter. We must remember the optical horizon, R sub h, refers to an imaginary situation for an observer who can detect both the emission and the detection simultaneously. That the instantaneous optical horizon is about 3 times the universe age for a flat universe, but this does not mean spacetime is being stretched. We presented some simple methods for calculating the distance from quasar galaxy emissions, again presuming a flat spacetime. Here is another example for Einstein lensing, another beautiful photograph from NASA. More summary. There is abundant evidence for curved spacetime being important for a proper description of our universe. Cosmological models presenting flat spacetime without reference to omega k, in other words, a curved spacetime, these models are really oversimplified. Even the notion that spacetime curvature can be described as a smooth function is probably too simple. And this is the end of our little universe, as provided by a figure from NASA of the cluster J1038. A beautiful, happy photo of Einstein lensing. Thank you for your time. Stick around for the credits and what's next.